Good morning. This is Dr. N. Ramya, Assistant Professor from Civil Engineering Department. Today, my lecture is on turbulence, how it is causing, what is the scale and its intensity in hydraulic engineering. So here, in previous lectures, we have seen what is the laminar flow and what is turbulent flow and what is the difference between them and what making the flow to become a turbulence, how it is transition is taking place from laminar to turbulent. All these points are discussed in previous classes. So here, in this lecture, we are seeing what is the cause and scale and intensity of the turbulent flow. Right. So here, as we already discussed, that laminar flow is having a Reynolds number less than 2000 and turbulent flow is occurring when your Reynolds number is greater than 4000, right? So here, this flow is classified are based on a Reynolds number, right? So if the Reynolds number is what? Reynolds number is inertia force by viscous force. Inertia force by viscous force, right? Viscous force. So here already we know this formula also, rho v d by mu is a Reynolds number, right? So here this by the Reynolds number, we are differentiating the flow. If the Reynolds number is less than 2000, then we are classifying that laminar flow as laminar, and turbulent flow, if Reynolds number is 4000, then the flow we are calling it as a turbulent flow, right? So here, laminar flow is it is a very smooth and orderly and regular, and it is having a streamlined path flow. But coming to a turbulent flow, the flow is irregular and there is a sudden change in the flow, right? So here the turbulent flow is mainly used for the mixing purpose. We have seen applications also, right? There is a complete mixing of fluid because of the particles jumping from one point to other point, so due to this complete mixing of fluid, due to the collision of fluid masses with one another. So here in this figure, it is very clearly seen that if these dots are your particles, it is not moving in a straight line. It is jumping. It is colliding one to other particle in irregular manner. So it is moving one point to the other point, other point to the other point, right? So it is what it is happening, right? And the fluid masses are interchanged between adjacent layers. The fluid masses are interchanged between adjacent layers. So here, the fluid masses in adjacent layer have different velocities. Interchange of fluid masses between the adjacent layers is accompanied by the transfer of momentum, which causes additional shear stress of high magnitude between the adjacent layers, right? So the particles which are moving in their own paths without disturbing the other particle adjacent to in parallel paths, that is a laminar flow, right? If the particle is interchanging because of the different velocities, because of the change in velocities, what happening? That fluid masses is interchanging their position. Due to this, we are seeing a transfer of momentum, which causing the additional shear stress of high magnitude between the adjacent layers. So due to this, we are seeing a turbulence in a fluid flow, right? So the shears in turbulent flow is mainly because of the momentum transfer. Because of the momentum, it is moving to other, it is other like this formation of eddies. There is more energy loss because of these irregular and there is sudden change in a flow. This because of these the descent layer is getting disturbed because of the transfer of momentum, and due to this we see a flow as a turbulence in a fluid flow, right? So here the shear in turbulent flow is mainly due to the momentum transfer, right? Momentum transfer. The contribution of fluid viscosity to total shear is small. Yes, the contribution of fluid viscosity to shear stress is small and is usually neglected, right? Is usually neglected. So here, in case of laminar flows, because of the definite functional relationship between shear stress due to the viscosity and velocity, right? And and in previous classes also we have seen the shear stress diagram of a laminar flow, right? The if velocity profile is a parabolic, then what about the shear stress? Shear stress is a maximum at the boundaries and complete shear stress is minimum at the center. Whereas here velocity is zero at the boundaries and velocity is maximum at center, right? Velocity is maximum at the center and velocity is zero at the boundaries. But coming to this shear stress, the boundary is having the high shear stress and minimum is at the center, right? So here it has been possible to derive a mathematical relationship for evaluating the energy dissipation of our frictional head, but such a simple relationship does not exist for turbulent flows. So here, uh, in laminar flow, just now we said that it is parabolic and this is your shear stress. This is your shear stress diagram, right? This is your shear stress diagram and this is your velocity distribution diagram. For laminar flow, this is for laminar, this is for laminar flow, right? Now for turbulent flow, now we see a turbulent flow here, right? Turbulent flow, the velocity diagram is logarithmic, right? Velocity profile is logarithmic for turbulent flow, right? And this shear stress is a very complex relationship. This exists a very complex relationship and it is very difficult to find out the relationship to evaluate the turbulent flow friction head for turbulent flows. However, to solve some of the practical problems, efforts have been made to evaluate semi-empirical theories of turbulence. So because of this complex diagram, here some mathematical expressions will be there. So these some simple empirical theories to to solve the turbulent application. Right? So this is what your laminar flow is. See how your flow is getting changed. Right? This is your laminar flow and this small portion is getting changed into transition state. See, this is how your complete flow is get in the form of turbulent flow. This is what a transitional state flow is getting, transferring from laminar to turbulent, right? So here, this is what the velocity distribution diagram in turbulent flow is more uniform than in a laminar flow. So here this blue one is your velocity diagram for laminar flow. It is parabola and this turbulent flow is a logarithmic for turbulent flows. Velocity diagram for turbulent flow is logarithmic. It is logarithmic, right? So it is not uniform. This laminar flow is not uniform. Here we are saying laminar parabolic, and here we are coming to the velocity distribution. We are saying some uniformity in some places. At boundaries, it is again there is no flow, and after that we are seeing the uniformity of the velocity distribution in turbulent flow. So in turbulent flows, the velocity gradient near the boundaries, the velocity here near the boundaries shall be quite large, resulting in more shear. Quite large, resulting in more shear. Right? The turbulent flows are the flatness of velocity distribution. Here, the flatness of velocity distribution curve in core region away from the wall is based on the mixing of the fluid layer. This logarithmic is based on your mixing and in the interchanging of the momentum. So here this mixing of the fluid layers, how well the fluid layers are getting mixed, and what is the exchange of the momentum between the particles, between the layers. Due to this, we say that the flatness of the velocity distribution curve for turbulent flows. So here the velocity distribution is paraboloid in laminar flows, tends to follow power law and logarithmic law in turbulent flows. Right, here we are saying that parabolic, and here we are saying logarithmic. It is using by the logarithmic law or power law for turbulent flow to draw a velocity distribution diagram, right? So the random orientation of fluid particle in a turbulent flow gives rise to additional stresses. We are seeing some additional stresses comes into picture for turbulent flow because of the complexity of the nature of the turbulent flow. So here the term additional stresses, the term we are calling as a Reynolds stresses. We are calling that as a Reynolds stresses. The formation of eddies, mixing, curving of path lines in a turbulent flow results in a greater frictional losses. For the same rate of discharge, viscosity, and the pipe size. Because of the eddies, because of the mixing and the curving of the path lines in a turbulent flow is much greater than the frictional losses for the same rate of discharges, pipe, and also a viscosity. Right, here are the turbulent motion can be classified as follows. One is wall shear, free turbulence, and convective turbulence. So wall shear, first wall shear, it occurs in immediate vicinity of the solid surface and in the boundary layer flow where the fluid has a negligible mean acceleration at the boundary. If it is a pipe, at wall, this wall turbulence. At wall, this is a wall turbulent at immediate vicinity of the solid surface. This is a wall turbulence. Here free turbulence, it occurs in a jets, wakes and mixing layers with etc. So free turbulence is, there is not much effect of these at boundaries. We are not inside the pipe because of the boundary. There is no effect for the free turbulence. Inside the, we are neglecting these boundaries and we are taking only the inner part, the inner turbulence, that we call as a free turbulence. We call that as a free turbulence. Convective turbulence, it takes place where there is conversion of potential energy into kinetic energy by the process of mixing. So this convective turbulence is what? There is a conversion of potential energy to the kinetic energy by means of mixing. That is the convective turbulence. The turbulent flow in annular space between the concentric rotating cylinder, conventional flow between parallel horizontal plates, etc. These are the examples of how these potential energy is getting converted into kinetic energy. Right? So here high flow velocities. Because of the high flow velocities also, there is a change of the flow from laminar to turbulent. So because of the speed of the fluid increases, so the inertia force also increases. Right? At higher velocity, smaller disturbance is amplified, leading to turbulence. Right? Sudden change in a flow direction. If there is a sudden change in a flow direction, then there also we see the turbulence, because at shapes, at bends, at elbows, our turns causes a flow separation. At these bends, there we are seeing some of the separation. They causes a flow separation. This flow loss its ordinary nature and turns chaotic. So here obstructions in path, flow paths. If there is any obstructions also, they will see some turbulences, right? So any object can disturb the streamlines and causes the turbulent wakes behind it. Examples what they have given: any cylinder in a river, car on a road, right? Sudden change. If the flow is moving in a laminar flow in a streamline, if there is any disturbances in a flow, it starts changing its position, right? This also will create a turbulence, right? This is what a obstructions in a path of flow is. Surface roughness. So rough boundaries disturb near the fluid layers, promoting transition to turbulence because of the boundaries also. In transition from laminar to turbulent flow also we have seen this bond. Surface roughness plays an important role. Right? Then high Reynolds number. If there is a high Reynolds number, then the flow is laminar. And if the Reynolds number is less, then we say that it is a laminar flow. Inertia force is very important. Inertia force also plays a major. If inertia force is high, if your Reynolds number is also high, it is creating a turbulent and leading to unstable turbulent flow. And these are the characteristics of your turbulent flows. Characteristics is what? Irregularity. Flow is because of the random movement of the particle from one to other plate. We see the irregular motion and irregularity in the flow. Flow variables like velocity, pressure fluctuate randomly. Velocity is not constant throughout the flow because of the turbulence nature. Velocity is more in some parts and velocity is less in some parts. Then we see the fluctuations. If velocity increases, your pressure decreases, pressure increases, both are vice versa. Right? Diffusivity is rapid mixing of fluid properties. Heat, momentum, rapid change in a fluid properties. Right? A three-dimensional vorticity, rotational motion and eddies in all directions. Vorticity or rotation in we see all directions. Right? It is in 2D. In all directions we see in three-dimensional vorticity. The dissipation of kinetic energy, reducing the energy from the larger eddies transferred to smaller ones, eventually converted to heat through viscosity. Right? Here turbulence occurs across a range of scales. Causes we have seen completed, now scales. So wide across scales are large scales, intermediate scales and smallest scales. If eddy is comparable to the size of the obstacle or flow domain, if it is more, we call it as a larger scales where energy transfer from larger to smaller eddies occurs. The smallest one where viscosity dominates, converting kinetic energy to heat, is the smallest scale. So each scale contributes to the overall turbulent behavior. Each will contribute to the overall turbulent behavior in a fluid flow. So here we are saying now what is large scale is also called as an integral scale. Integral scale, the definition is largest eddies that obtained energy from the mean flow. Largest eddies, largest eddies is obtaining from the energy from the mean flow. Right? The controlling the characteristics is what? Control the overall transport of momentum and energy. Overall transporting from the particle changing from one to other part. So overall transporting of momentum and energy. So depending on the geometry and the boundary conditions also plays it is a small, a scale or large scale. Example is large squirrels behind a bridge pier. Large squirrels behind a behind a bridge pier. So here illustration is show large eddies forming behind an obstacle. After obstacle, there is large eddies formation. So here another scale, it is Taylor's intermediate scale, right? So here the intermediate scale is what? The transitional eddies where both inertia and viscous forces are significant, right? Here the importance is predicting energy transfer rates and turbulent mixing. Application appears in empirical correlation and turbulence model like RANS. What is RANS here? Reynolds. RANS is Reynolds average Navier-Stokes equation. Navier-Stokes equation. RANS model is Reynolds average Navier-Stokes. And here the smallest one is Kolmogorov. Smallest scale, the smallest eddies where viscous effects dominates and energy is dissipated into heat. Here, this small scale is the smallest eddies where viscous effect dominates and energy is dissipated into heat. The formula for this is neta is equal to V cube by E whole to the power of 1 by 4, right? So, on V is the viscosity. Here V is the viscosity and rate of energy dissipation is E, right? So this is what your formula to calculate the smallest scale of the turbulence. The flow is smooth. Again, kinetic energy is converted into thermal energy. Turbulence intensity. Here the intensity is what? It is the ratio. Intensity is what? It is a ratio of velocity fluctuations to the mean velocity at a point in a flow. So what is this intensity is? Velocity fluctuations, that is velocity dash by your mean velocity, average velocity, right? So what is that equation is? U dash by U bar is your intensity. To find out the turbulence intensity, that is the ratio between the velocity fluctuation to the mean velocity at the point in a fluid flow. Here is the formula. Ti is U dash by U bar into 100. Right here, U bar is the root mean square of the velocity fluctuations, and U is your U bar is your U is your mean velocity. Categories also here given. If that is 0 to 5%, when you come do your values, if the values is given, then you will get the intensity. If the intensity percentage is 0 to 5, then we call it as a low category, and it helps in clean and industrial airflow. And here the medium is 5 to 20%. We call it as a medium, and it is for natural ventilation. And here high is the greater than 20% is the high, then we call it as awake regions and urban winds. Intensity of the turbulence. How we are measuring here? So intensity of turbulence is measured by hot wire anemometer, laser Doppler anemometer, LDA, and pitot static tubes, CFD simulations. By these four methods, we can measure the turbulence intensity, right? So here, hot air anemometer, it measures the rapid velocity fluctuations using in a heated wire. And a laser Doppler anemometer is non-intrusive, uses laser light scattering. And a pitot static tubes is approximate method for mean fluctuating pressures. We use this for pitot static tubes. And CFD simulation is computational fluid dynamic model. Again here we create a geometry, mesh, and all. Here we are using turbulent models as here RANS model, because Reynolds average Navier-Stokes model and large eddy scale, this DNS model. These are all this is numerical model, So these are the models used to find out the turbulence of the flow. And here are some practical examples of the turbulence. Is airplane wings. Smoke from a candle causes lift fluctuations. Airplane wings are used to causes lift fluctuations. And smoke from a candle transitional from laminar to turbulent. Water around bridge pier creates large wake vortices. Large wake vortices. Blood flow in arteries can turn turbulent at high pulse rate. These can turn turbulent at high pulse rate. Wind around tall buildings generates turbulent wake zones. These are all practical examples of the turbulence. Here are the effects of turbulence. How it is affecting: increased mixing, higher drag, enhanced mass transfer, noise generation and structural vibration. These are the effects. These are the effects of turbulence. Right? Increased mixing enhances heat and mass transfer rates. Higher drag, higher resistance, affecting vehicles and pipeline efficiency. Right? Because of the increased resistance affecting the vehicles and pipeline efficiencies. And enhanced mass transfer is useful in combustion and chemical mixing. Causes by rapid pressure fluctuations. Noise generation is caused by rapid pressure fluctuations. Structural vibration, unsteady forces causes fatigue. These are all the effects of the turbulence. And model turbulence, too complex for direct calculation at all scales. Right? So direct numerical simulation, DNS, large eddy simulation and Reynolds average Navier-Stokes equation. Right? These will resolve all scales, very expensive computationally. Direct numerical simulation is very expensive. And here large eddy simulation computes large eddies, model small scale. And here average effects in Reynolds averaged Navier-Stokes Rans equation, averages effects of turbulence and practical for engineering problems. And here are the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.